Hey guys, so talking about combustion analysis. So we haven't talked much about what combustion is, but we can get an introduction here. And we're talking about, right, a hydrocarbon undergoing complete combustion. And we have, hydrocarbon means that you have a carbon-containing compound and a hydrogen-containing compound. Or a carbon and hydrogen containing compound. But it doesn't specifically tell us how much of our carbon and hydrogen, so we can make a formula showing that we have some X amount of moles of carbon for every Y amount of moles of hydrogen, right? So that would represent what our mole-to-mole ratio is for the formula. We use X and Y because we can't assume that they are the same amount. If they happen to be the same amount, that's cool, but we can't assume that off the bat. So we have this sample of hydrocarbon undergoing complete combustion, and we're producing carbon dioxide and water. So we can show it can't be a complete balanced equation because I don't know how much carbon and hydrogen there is, but we can write an equation where we have the hydrocarbon, and what it means to undergo combustion is reacting with oxygen. And that's going to be true about any combustion. So when you see those words combust, it just means whatever you're talking about is reacting with oxygen. And we are going to produce carbon dioxide and water. Now, it doesn't matter how many carbons and hydrogens you have, but if you have a hydrocarbon reacting with oxygen, it will always produce carbon dioxide and water, and we'll talk about this later on in the unit, but it's kind of an important reaction in our lives. It produces energy. We see it in our cars. They're called, for the most part, called combustion engines. This question is asking us to find the empirical formula, which, if we recall from the beginning of when we came back from break, empirical formula means the simplest whole number ratio. Well, I'll be more specific, mole ratio of our elements. So what we're trying to find is that whole number ratio. Is it C2H4, is it C2H6, whatever it is, but we're trying to find that number. So if you go back into your notes and go back in, right in the slides, remember that we had a process for finding the empirical formula. We took the percent composition and we turned the mass into moles, and then we took the ratio of the moles. In this case, we have masses, but it's not masses of pure elements, it's masses of compounds. So we have to think about our problem solving and understand how we can find our moles of carbon and our moles of hydrogen. So I'm going to put carbon in red and hydrogen in green. And we can utilize our understanding of the law of conservation of matter, saying that matter can't be created or destroyed. So if I'm thinking about carbon in this reaction, we have carbon from the compound, and it's reacting with oxygen, and it's forming carbon dioxide and water. There's only one place on the reactant side where carbon is, and it's in the compound. And that's what I'm interested in. I want to figure out how many moles of carbon there was in there. And on the product side, there is also only one place that carbon went to, right? So all of the carbon from the reactant side goes into carbon dioxide. So if there's a way for me to figure out how much carbon is in the carbon dioxide, then I can say that all of that carbon must have come from the carbon dioxide. So lucky for us, they tell us that there is 4.40 grams of carbon dioxide. And if I do a little dimensional analysis with our understanding of how our compounds work, right, for every 1 mole of CO2, there's 44.01 grams of CO2. Now, from here, since I now have it in terms of moles of the formula, I understand how formulas work, and we can say for every 1 mole of CO2, there must be 1 mole of carbon. And remember, we said all of that carbon must have come from the compound. So I'm kind of working backwards to figure out how much carbon was in this hydrocarbon. And when I do this, we essentially come to 0.100, 0.099977, right? That works out to that, moles of carbon. And I'm going to stop and ask myself, why did I do that? And I'm looking for the empirical formula, which is the simplest whole number ratio of elements in the compound. So I now know how many moles of carbon were in the compound. So if I could find the amount of hydrogen that was in the compound, we could then take the ratio of the moles to the hydrogen. So again, we can look and see that the hydrogen is in only one place on the reactant side, and it's all in the hydrocarbon, and it is only in one place on the reactant or on the product side in the form of water. So all of this hydrogen must have gone into the water. And using the same idea, right, where they give us the amount of water, 2.70 grams of H2O, using the same idea that if I can turn it into moles of water, and then I know that for every 1 mole of water, there's 2 moles of hydrogen, we can figure out how many moles of H2 there was. So for every 1 mole of H2O, 18.02 grams. And then for every 1 mole of H2, I'm just using the formula as the conversion factor here. So we can do this, 2.7 divided by 18 times 2. We get 0. And if we're thinking about sig figs, 3000 moles of H. And just because we should show it, this was step 1 of our finding empirical formulas, was turning our amounts into moles of the elements in the compound, and step 2 is taking the ratio of those moles. So we're going to divide through by the smallest amount, and again, I know I really shouldn't be doing this because the mental math is there, but we can show the process that for every 1 mole of carbon, there is 3 moles of hydrogen. And those are whole number ratios. So I have nothing else to do here. It's when we do this part and we don't get whole numbers that we have to start doing other things. But since we're just looking for the empirical formula, the simplest whole number ratio, we get CH3. Now, a question I could also ask you is this compound, is this also the molecular formula? And you should be able to tell me no, because this isn't an HONC 1234 approved formula, right? If we do this, we realize that this cannot be a viable compound. So this would only be the empirical formula. We would need to have a little bit more information to find the molecular formula, but since this is just asking for empirical,